Training a machine learning model involves selecting the right algorithm, preparing data, and setting hyperparameters. Evaluation uses metrics like accuracy and F1 score to assess performance. Improvement focuses on techniques such as cross-validation and hyperparameter tuning to enhance model accuracy and robustness. Understanding these principles is crucial for developing effective models. Training a machine learning model involves understanding how algorithms learn from data, measuring success, and refining performance. This module covers the life cycle of model development, from initial training to evaluation and optimization. We'll delve into mathematical foundations, performance metrics, and strategies to tackle challenges, equipping you to develop and improve models effectively. Model training involves hypothesis functions mapping inputs to outputs, loss functions quantifying errors, and optimization algorithms reducing these errors. Evaluation metrics differ for classification and regression tasks, with accuracy, precision, and recall for classification, and mean absolute error, mean squared error, and R-squared for regression. Address overfitting and underfitting, and use hyperparameter tuning and ensemble methods for robust models. Model training is the process where algorithms learn from data by adjusting parameters to minimize errors. It involves the hypothesis function mapping inputs to outputs, the loss function quantifying errors, and the optimization algorithm reducing those errors. This feedback loop refines models, enabling accurate predictions on new data. The hypothesis function transforms input features into predictions, crucial for tasks like spam classification or house price prediction. The loss function measures prediction errors, using metrics like mean squared error or cross-entropy. Optimization algorithms, notably gradient descent, iteratively adjust parameters to minimize these errors, enhancing model accuracy through iterative learning cycles. Gradient descent is crucial in machine learning, akin to navigating a foggy mountainside. It calculates the gradient of the loss function, adjusting parameters in the opposite direction. The learning rate determines step size, impacting training speed and model quality. Key considerations include avoiding overshooting with high rates and slow training with low rates. Model evaluation metrics are essential for assessing performance. They allow comparison of models, identification of weaknesses, and informed deployment decisions. The choice of metric depends on problem type, such as classification or regression, and business objectives. Factors like class imbalance and cost sensitivity also influence metric selection, making it as crucial as the modeling process. The confusion matrix is foundational, detailing true positives, negatives, false positives, and negatives. Accuracy measures correct predictions but can mislead with imbalanced data. Precision is vital when false positives are costly, while recall is crucial for identifying all positives. The F1 score balances precision and recall, and receiver operating characteristic area under the curve evaluates model discrimination across thresholds. For balanced datasets, accuracy is effective for evaluating model performance, such as predicting coin flips. In imbalanced datasets, precision, recall, and F1 score are crucial, especially in fraud detection or disease screening. Receiver operating characteristic. Area under the curve is ideal for threshold-agnostic evaluation, offering insights into model discriminative power, useful in ranking problems or holistic model comparisons. Mean absolute error, MAE, measures the average absolute difference between predictions and actual values, robust to outliers. Mean squared error, MSE, and root mean squared error, RMSE, penalize large errors, crucial in scenarios like demand forecasting. R-squared indicates the proportion of variance explained by the model, useful but potentially misleading with non-linear relationships. Addressing model challenges involves tackling overfitting and underfitting, key aspects of the bias-variance trade-off. Overfitting captures noise, while underfitting misses patterns. Both hinder performance. Techniques like cross-validation, regularization, and model complexity adjustments help mitigate these issues, ensuring models generalize effectively to new data. The bias-variance trade-off is crucial in machine learning. High bias results from simplistic assumptions, leading to underfitting. High variance arises from sensitivity to data fluctuations, causing overfitting. The goal is to achieve a balance with low bias and variance, ensuring accurate predictions on both training and unseen data, exemplifying a well-generalized model. Overfitting occurs when a model performs well on training data but poorly on test data, memorizing noise instead of learning patterns. Mitigation includes regularization to penalize complexity, adding more training data, simplifying models, selecting relevant features, and early stopping to prevent overfitting. Underfitting occurs when models are too simple, lacking the capacity to capture complex patterns. Causes include overly simple models, insufficient features, over-regularization, and inadequate training. Solutions involve increasing model complexity, enhancing feature engineering, and reducing regularization. These adjustments help models better capture underlying data patterns, improving performance and generalization. Hyperparameters, unlike model parameters, are predefined settings that guide the learning process, such as learning rate, tree depth, and regularization strength. Effective hyperparameter tuning is crucial for model optimization, as it systematically searches for configurations that enhance performance, transforming models from mediocre to exceptional by leveraging structured search strategies. Grid search evaluates all hyperparameter combinations, offering thoroughness but at high computational cost. Random search, by sampling randomly, often finds near-optimal settings faster, focusing on impactful parameters. Bayesian optimization uses probabilistic models to guide searches intelligently, learning from past evaluations, making it efficient for costly models. Feature selection is crucial for enhancing model performance by retaining only predictive variables. Filter methods use statistical tests to evaluate features independently, while wrapper methods assess feature subsets through model training. Embedded methods, like lasso regression, integrate selection during training, balancing efficiency and accuracy. These strategies reduce noise and computational costs, improving generalization. Ensemble methods enhance model performance by combining predictions from multiple models. This approach reduces variance and mitigates weaknesses of individual models. Bagging, like random forests, trains models independently, averaging predictions to reduce variance. Boosting, such as gradient boosting machines, builds models sequentially, focusing on correcting errors, thus reducing bias. Both strategies excel in various applications. Bagging trains multiple models on random subsets, combining predictions through averaging or voting. Random forests exemplify this, reducing overfitting and variance. Boosting builds models sequentially, focusing on correcting misclassified examples. Gradient boosting machines and XGBoost excel here, reducing bias and variance. Bagging suits high variance models, while boosting is ideal for high bias models. Model training, evaluation, and improvement are central to machine learning. We've delved into hypothesis functions, loss functions, and optimization algorithms. Key challenges like overfitting and underfitting are tackled through regularization and feature engineering. Hyperparameter tuning and ensemble methods enhance model performance, ensuring robust solutions tailored to specific tasks.